Hi, good afternoon. This is Mr. Cassidy, and today I'm going to be covering Chapter 3, Lesson 1, learning about constant rates of change in linear relationships. Now, this chapter is all about relationships, so instead of just solving for x, now we're going to look at two things to go together. Say you're filling a bathtub, and every minute you're adding more water. Well, we're going to look at the relationship between two quantities now, say the minutes and the amount of water. We're going to be representing that on graphs and on tables. And you can find this in your book starting on page 172. Page 172 is where you're going to follow along with this today. So, without further ado, let's go ahead and dig into it. Thanks. So, in 6th and 7th grade, you studied ratios previously. And for example, we did ratios about things like this. Say for every 5 children in Folsom, the library has 10 books. We learned that you could write a ratio like this. By writing 5 colon 10, we mean 5 kids for every 10 books. And we could also express that same ratio as a fraction. 5 kids meant the same as 10 books. Well, we're going to extend this idea of ratios. So this would be the relationship between the number of kids and how many books the library has. We could look at it now as a table where there's different amounts of kids and different amount of books at the library, and we can also put that on a graph. So let's say kids is my x-axis. I'm going to put 1 kid, 2 kids, 3 kids. Oh, sorry. Let me backtrack a tiny bit. Let's put 5 kids here, 10 kids here, 15, 20, 25, and 30. And then I'll put the number of books on the y-axis. 10 books I'll put here, 20, 30, 40. So what happens if I graph those coordinates? So when there's 5 kids, there's 10 books. That's going to be a single dot on the graph here. 10 kids was 20 books. That's going to be right here. 15 was 30. And 25 kids meant 40 books at the library. Do you notice what's formed as I'm graphing this? It should be pretty clear that this is slowly starting to form a straight line, which isn't easy to draw with my tablet, but we could extend this line and continue to see the relationship is pretty much a very straight line on a graph. Well, we have a word for that, and this lesson is all about that word. We call it linear. Luckily, this is an easy word to remember because linear has the word line in it. And so what that means is we're forming a straight line on the graph. Now, in order to figure out whether it's a straight line, it has to be a straight line if it's following a constant ratio. So the constant ratio here is 10 more books, 5 more kids, 10 more books, 5 more kids, 10 more books, 5 more kids, and so on. What we're trying to do is analyze tables and graphs and determine first, are they linear? By seeing, is it a constant ratio like that? And in order to do that, afterwards, we can then say, well, what's the rate of change? And the rate of change is the ratio that we're able to find. So let's dig into it. Here's our example problem. Here we've got a balance in an account. Here's your bank account, say, and you've got a number of transactions on the left-hand side. I do like to label things X and Y. And guys, X is always on the left. It goes in order. X comes first, Y comes second. So to analyze this, we could put it on a graph to see if it's linear, but there is an easier way. Without having to graph all this, we can actually just find the rate of change. So I have to ask myself, how much is the Y changing? Change in Y. That's going to form the numerator of my ratio. And then how much is the X changing? That's going to form my denominator. So how much is the Y changing? Go from 170 to 140. I see that it's going down $30. Awesome. That's my numerator. I go ahead and you can do the whole thing at once right now. Down 30. From 140 to 110, it's down 30. And from 110 to 80, it's down 30. Awesome, it's going down by 30 each time. Let's take a look at the number of transactions. From 3 to 6, it's up 3. From 6 to 9, it's up 3. And from 9 to 12, it's up 3. So now let's write that change as a ratio. The very first set, and I'm going to put a box around them, minus 30 over plus 3. Minus 30 over plus 3. Sorry, my tablet's a tiny bit streaky. I think I've been using it too much. Minus 30 over plus 3, that is my ratio. And what I want to do, I could simplify that and make it minus 10 over 1. That's going to be my ratio. And I need to see, was it a constant ratio each time? Was it going down by 10 every up by 1? Well, yeah, it was the same because, see, each of these ratios, minus 30 plus 3, minus 30 plus 3, those are the same. Now, how can we tell? We always go for these outside numbers, the change, to make our ratio. And if they all match, or if they can be reduced to the same fraction, then it's linear. So this would be a linear graph. Second, what we can also tell is what is the ratio, or what is the constant rate of change here? Well, it's going down 30 for every 3 transactions. Let's change that, simplify it. It's going down $10 for every transaction. $10 for every transaction. Okay. If you wrote down $30 for every 3 transactions, that's fine. Right now, I just want you getting the hang of, can you see, is it a constant rate of change? And therefore, is it linear? So it's your turn. First, let's label X and Y. Here's a babysitter charging money. And what's the ratio? How much does it change from 10 to 18? You should have said plus 8 here. And how much does the hours change that corresponds? You should have said plus 1. Okay, make a ratio there. 8 over 1. Let's see if it's constant. How much does it change from 18 to 26? Okay, that's plus 8. How about from 2 to 3? It's plus 1. Okay, so that equals 8 over 1. Same ratio so far. How about from 26 to 34? That one's plus 8. And 3 to 4, that one's plus 1. So we've got the same ratio each time. Is it linear? You should have said yes. Yes, it is linear because we got the same ratio each time. 8 over 1. Now, what's the rate of change? What's the constant rate of change in this problem? I'll abbreviate ROC for rate of change. We should have said $8 for every 1 hour. Now, if you did it the opposite, if you said for every 1 hour there's $8 more, that's totally fine. Right now, we're just trying to get the idea of it's the change on the outside. We're not really worried about what those numbers are on the inside. It's more about how we add or subtract to get to each new number or pair. All right, how about this one? Go ahead and decide for yourself now. If it's sideways, we can just do X on top, Y on the bottom. And so let's first find the change in Y. Well, each of these are going up by 1, plus 1, plus 1, plus 1. So decide for yourself, is the ratio constant? And therefore, is it linear? You should have said yes. Yes, this is a linear relationship because the ratio is always plus 9.8 over 1. Sorry, plus 1 over 9.8. Now, what does that mean in English? What's happening here? Well, it's the speed in meters per second in the time since the ball is dropped. So the speed is increasing. but it's increasing at the same rate. So every second it increases, you should say every second it increases by 9.8 meters per second. Okay. Meters per second. All right, carrying on. So your turn. Try problem A. Is it linear? You should have said no, and here's why. When we go from 95 to 90, it's adding 5. And when we go from 5 to 10, it's adding 5. Oh, sorry, 95 to 90 is subtracting 5. I should be clear about that. And minus 5 over 5, that would reduce to a negative 1. But is that the same all the way? Well, no. The very second time here, 90 to 86 is minus 4, and this is plus 5. Minus 4 over 5 is not the same fraction, so we would say no, this is not linear. Now, how about our second problem? What are we going to do here? We're going to make the table. Here I'm going to go ahead and put maybe number of volunteers is my x, so I'm going to put x here, y here, and I'm just going to write down their values. So when x is 8, y is 80, because I just follow the lines all the way up and over. And when x is 16, y is 60. And when x is 24, y is 40. Well, is this a linear relationship? You decide. You should have said yes. It is linear, and one way we can tell is this is a straight line on the graph, but the other way we can tell is by looking at these values. So what's the rate of change here? Well, here this is subtracting 20 and going up by 8, so it's minus 20 over 8. And what does that mean here? It means they're going down 20 volunteers every 8 minutes. Oh, as it goes down 8 minutes. All right, carrying on. Let's go ahead and continue. So it's your turn to practice. We have several different tables. They organize them a little differently each time. But let's start with problem 1. Is this a linear relationship? Be careful here. Make sure you reduce the rate of change each time to see if it's the same. You should have said yes. Yes, this is linear. And here's why. When I find the rate of change here, the cost is going to be my y. The time will be my x. 15 going up to 24, that's adding 9. And 5 going up to 8 is adding 3. So 9 over 3, both are positive, and that reduces to 3 over 1. All right, how about 24 to 36? 24 going up to 36 is plus 12, and 8 going up to 12 is plus 4. 12 over 4 is the same as 3 over 1. So I actually get the same ratio here. I get the same in the last one too. It's adding 36, and here it's adding 12. 36 over 12 is the same as 3 over 1. I have the same ratio all 3 times, so yes, this is linear. Now, second part of the question. What is the ratio, or what's the relationship between cost and time here? Well, you would want to say something like this. For every hour, there's 3 more dollars, or for every 3 more dollars in cost, or maybe it's cents, there's 1 more hour of use. So it's probably something like that. Oh, it looks like it is cents. So it's 3 cents for every 1 hour. Okay, how about problem 2? Is this a linear relationship? You should have chosen no. No, it's not. Wow, that got really streaky. No, this is not linear. Not linear. And the reason why is we've got a changing rate of change. Here, when I go from 4.9 to 19.6, if you go ahead and subtract them, you get something like 14.7. is being added as they add 1 second. And then the second one increases significantly more. It's like, I don't know, 24.7 is the numerator, and plus 1 is here. So notice the distance is increasing more each time, and the time is only increasing by 1 second. So no, it's not linear. And we can stop the problem there. How about our Italian dressing recipe? What's the rate of change here? Is this a linear relationship? You should have chosen yes. And if it would help you to think of these as decimals, it might. But basically, we've got an increase of 3/4 more cup of vinegar as 2 more cups of oil are added. Then we got an increase of 3/4 cup vinegar as 2 more cups of oil, and 3/4 cup more of vinegar for 2 cups of oil. So what's the rate of change? Well, it's pretty much already been said. It's 3/4 cup more vinegar for every 2 cups more of oil. All right. Well, carrying on. The last 3 problems we're going to look at, again, this is on page 174-ish of your book, maybe 175, so you can do it in your book if you'd like, is continuing the same question. Is it linear, and what's the rate of change? So for problem 4, we have water level and time. Is it linear? You should have said yes. Yes, it's linear. You can tell because there's a straight line there. Now go and find the rate of change. You're going to need to make an XY table and list those points, like x is 0, y is 0. That's this dot. And I like to use the ones that are on grid lines, so I'm going to put 2 and 4 here. So find the rate of change. You should have seen that it was adding 4 here and adding 2 here. So it's 4 over 2, which reduces to 2 over 1. The ratio here is 2 over 1, so that means 2 inches of water, because y was the water, for every 1 minute, because x was the minutes. 2 inches for 1 minute. All right, next problem. Is this a linear relationship? You should choose yes. Yes, it's linear because each of these form a straight line. It's going up at the same ratio. So what's the rate of change here? Again, make your own XY table to find out. Oh, and when things aren't labeled, you may need to find on a grid, like here it jumps from 0 to 30, that this line is 15 miles. So here you've got, when it's 2 inches on a map, it's 15 miles, and 4 inches on a map is 30 miles. So it looks like for every 15 miles increase, that's miles, for every 15 more miles, it's 2 more inches. 15 miles for every 2 inches. All right, last idea here. Is this one linear? You should have chosen yes, simply because they look like a straight line. Now go ahead and make your own table and decide, what is the rate of change here? Well, y is cost, and it's in dollars. X is people, and who knows, it's cost for a party or something. At 5 people, it costs $100. And at 10 people, it's a little tough to tell, so I'm actually going to skip ahead to 15 people and see. That looks like it's at $250. So what's the rate of change? Well, the cost is going up by $150 as the people go up by 10. So $150 for every 10 extra people. And we could actually reduce that to get, I don't know, $15 for every one person. All right, guys, that concludes our lesson on rate of change. Hopefully, you guys understand now the difference between linear and nonlinear graphs is whether it's got a constant rate of change. As we go forward in the unit, we're going to be exploring why are graphs helpful? Why do we use them? And how do they help us with math? All right, I thank your minds and your hearts, and I hope you have a wonderful afternoon. Bye.